And that was Moby singing We Are All Made of Stars. And he is introducing this week's episode of Wild Side, which is all about our solar system. And if you were listening last week, then you remember that I introduced the solar system in kind of a preliminary way, and I talked about some of the strange and unusual structures that we find in the solar system other than our planets, and now I'm ready to move on and think about the 8 planets, which of course were once 9, and think about all these different planets and the interesting things that characterize them and what makes them similar, what makes them different, and just kind of get to know our solar system a bit better. And of course, first on that list is Mercury, which is the closest planet to the Sun and also the smallest. It should be mentioned, though, that while it's smaller in diameter than many of the moons in our solar system, it's also more massive, so it does have quite a lot of weight that it packs into that small size. Now, this planet has been known since at least the 3rd millennium BCE, when it was observed by the Sumerians, and it has been referred to as both the morning and the evening star, which is also true of Venus, because people saw it at those times of day, and they thought that it was a star. They didn't realize it was a planet until we had equipment that allowed us to kind of look at and chart these things in greater detail. Now, Mercury is named after the god of commerce, travel, and thievery, and this is just the first of many different names that you'll notice are derived from Roman and Greek mythology in our planet, in our solar system. And some people think that maybe this name was chosen for the planet because Mercury it has a very speedy movement across the sky, and so it's kind of related to commerce and travel. Now, this planet has a highly eccentric orbit, which means that it doesn't quite behave in the sort of normal neutral way that some of the other orbits are in our solar system. And sometimes it can be as close to the Sun as about 46 million kilometers, if you can actually call that close. But at other times it can be as far away as 70 million kilometers. And so, of course, it does have quite different things that it experiences throughout this orbiting period, because as you get closer and farther away, that can change what's happening on the surface of the planet. Now, for a really long time, scientists were quite confused by these differences in the observed and predicted orbit. So they expected the orbit to be kind of nice and circular and kind of like our orbit, and they didn't find that, and they couldn't figure out why it was this kind of huge variation from the closest to the farthest from the Sun. And for a while they explained this by thinking that maybe there was an additional planet that was out there affecting Mercury's orbit. But in fact, the problem wasn't that there was something else that was affecting the orbit. The problem was with the calculations that they were using. So they were using just general Newtonian kind of calculations, and it turned out that what they needed to understand was the general theory of relativity. And once this was proposed, it was used to explain how Mercury moved, and this was one of the things that actually showed that the general theory of relativity was, in fact, probably a pretty good thing and made a lot of sense in our universe. And in case you're not familiar with it, and to be honest, I'm not really that familiar with it, basically it describes the motions of bodies that are in strong gravitational fields or near the speed of light. And in this case, of course, you've got a planet that's quite close to the Sun, which has a lot of gravitational pull, and that's why the theory of relativity works to explain Mercury's orbit. Now, even though it does have kind of a quick movement across our sky from our point of view, it has quite a slow rotation. And of course, the rotation is how often the planet revolves on its own axis. And this happens 3 times over a period of 2 years. And previously it was thought that the day length equals the year length on Mercury, and that was eventually found not to be true. But still, 3 times over a period of 2 years is incredibly slow. And for anyone standing on Mercury's surface, this would be quite a strange experience, not just because Mercury's surface is quite uncomfortable in many ways, but also because of the way that they would perceive the Sun. So because of Mercury's movement towards and also away from the Sun, as well as its revolution on its axis, you would have this really interesting experience where the Sun might be seen to rise and then kind of increase in size as it's rising and getting closer to the planet, but then stop, maybe move back a little bit, stop again, and then move forward and get smaller as it sets. And the exact experience would depend on where you were longitudinally, but no matter where you are, you would see this kind of dramatic variation, something very different from what we see when our Sun rises and sets throughout the day. You would also notice that the movement of the stars appears to be much faster than the movement of the Sun. And again, that's because of this strange, kind of very quick movement around the sun, but very slow revolution on the axis. Now, as you might expect, for a planet that is as close to the sun as Mercury is, it does have some very extreme temperatures. In fact, the most extreme in our planet in some ways. So it has lows of 90 Kelvin all the way up to highs of 700 Kelvin, all on a single planet. And Mercury is just one of many terrestrial planets. So the terrestrial planets are the ones that are in the inner portion of the solar system, and then after you get out of Mars and through the asteroid belt, you start up with Jupiter, and that's when you start having the gaseous planets. And Mercury has a heavily cratered surface that's very old. It doesn't have any plates, so it doesn't experience plate tectonics in the way that we do. And it has some enormously long and really high ridges, so it's got some really interesting topography. And many of these ridges cut through craters, and therefore, you can tell that the crater was left there before, and then something happened that made these ridges come up afterwards. But since they don't have plate tectonics, researchers think that probably what happened is that there was compression of the planet itself. So whether that has to do with something pushing from the outside or something pulling it from the inside, basically you've got the compression of the land, and when you've got all that pressure, there's nothing left to happen except some kind of wrinkles will form in the surface. And in fact, the surface area, the entire surface area of the planet, is thought to have decreased by 1 kilometer over time. And maybe relative to the entire planet, 1 kilometer is not that much, but it's still pretty impressive to think that you have had enough force to change the size and shape of the planet over some period of time. Now, there is some evidence that there's water that exists in the shadows of the craters found at the planet's north poles, which is pretty impressive when you think that this is as close to the sun as it is, and that it can not only have water but retain it in ice form. And that just goes to show that you do have these really extreme fluctuations. So where it's facing the sun, Mercury is obviously very warm, but in the shadowy bits that are away from the sun and they're in a shadow, it is in fact very cold. Now, one of the planet's largest features is the Calorus Basin, which is about 1,300 kilometers in diameter. And this was probably caused by an impact that occurred really early on in the planet's history. It's quite an old area of the planet. It also has areas of smooth plains that potentially result from volcanic activity, but there is not any volcanic activity currently, so this would have happened quite a long time ago. So the planet is somewhat like ours in that it has kind of nice, flat, subtle areas, but then also very intense, kind of rocky terrain. Now, Mercury is also very dense. In fact, it's the second densest major body in the solar system, right after Earth. And this is probably because it has an iron core, somewhat like ours, but larger than ours, relatively speaking. And it probably accounts actually for the majority of the planet. So it has less of a mantle and a crust than we do, and much more of a core. In fact, the core is 1,800 to 1,900 kilometers in radius. And again, just like last week, I know that these numbers are kind of hard to imagine, but I say them out loud because it is kind of impressive to hear this, how fantastically huge this is. Now, some of the core is probably molten, which you would expect given how similar it is to ours in many ways. And as I said, the mantle and crust are quite thin, so they're probably only about 500 to 600 kilometers thick altogether. And Mercury also does have a thin atmosphere, and the atmosphere is probably made up of atoms that are lifted off of its own surface. So when the solar winds come out and hit the surface, they'll scatter the atoms up, and they'll be captured in the atmosphere. Sorry. Now, the atoms can't be retained for very long because Mercury is so hot. So eventually all of that heat, all the activity of all that energy, causes the atoms to escape into space, but then they're continually replenished as more solar winds come along and scatter up more atoms. And so the atmosphere is basically kind of a young thing that's always being renewed by these astronomical activities. And in case you're interested in going out and seeing Mercury, you actually can do this with the naked eye, depending on the time of year and, of course, how nice the night sky looks near you. You also can see it with binoculars. However, it can sometimes be difficult to see because of its close proximity to the sun. So you're only going to be able to see it when there's enough space between the two that you can kind of distinguish it from the glow around the sun. And we do tend to see it often kind of at the extremes of the day, so right around sunset and right around sunrise, because that's when the sun is out of the way long enough for us to be able to distinguish Mercury. And that was the wonderful Kathleen Edwards singing Mercury. Of course, not the same Mercury that I was just talking about, but Mercury nonetheless. Now the next planet on the list is Venus, and Venus, of course, is the second planet from the Sun, which is why it's the next one on our list. It's also the sixth largest planet in our solar system. Now Venus also has been known for quite a long time, at least since prehistoric times, and that's thanks to the fact that it is the brightest object in the sky, right after the Sun and the Moon. Now, as I said before, it's also known as both the morning and evening star. So back in the day, it was sometimes known as Eosphorus or Lucifer, and that was the morning star, or Hesperus, and the evening star. And then finally people realized that actually this was the very same thing, and it was in fact not a star at all, but a planet. Now Venus has the most circular of all the orbits of the planets, but it does have a very unusual rotation. So somewhat like Mercury, it has a very slow rotation. 243 Earth days will pass in a single Venus day. And in fact, Venus's year is shorter than its day. Another interesting thing is that it's retrograde, which means that it moves in a clockwise direction if you're looking down on it from the North Pole. And this is only true of a few planets in the solar system, as I said last week. Most of them do move in a counterclockwise motion, and this is one of the few that moves in a clockwise direction. Now, in Venus, the period of rotation and orbit are synchronized, which means that we see the same face of Venus each time the Earth and Venus come to their closest. So we don't ever get a view of the far side whenever we are coming up near it in our orbit. So we have to send out satellites in order to see good, clear pictures of the other side. Now with Venus, like with the Moon, we can see really dramatic phases. And this was observed notably by Galileo, potentially also by other people before him, but certainly it was famous. Galileo's observation was famous because he used this to support Copernicus's theory that the Sun was the center of our solar system and that all the other things moved around it. And he was saying that just as the Moon revolves around us and therefore has these phases that we see, this would suggest that because Venus has these same phases, Venus must move around something, and most likely that thing was the Sun. Venus is sometimes called Earth's sister planet, and part of the reason for that is that they do have very similar sizes. So the diameter of Venus is about 95% that of Earth, and the mass is about 80% that of Earth, which in kind of astronomical terms is quite close. When you think about the huge size and the tiny size of some of the other planets, this is actually very similar. The two planets also both have relatively young surfaces, and you can tell that by looking at the craters. So the fact that there are any craters at all, and also the date at which those craters were made. And the two planets have similar densities and chemical compositions. However, even though we have all these same characteristics and we have life, it's probably not the case that there was ever life in Venus's clouds. And people thought early on that maybe this would be the case, that there were some conditions in the clouds that might have made it favorable for life to spring up. But actually it has since been found that Venus might in fact be the least hospitable place in our entire solar system, which is pretty impressive when you think about the far planets and how distant they are from the Sun, and therefore how extreme their temperatures might be. And also, as I'll talk about a little bit more next week, the gaseous planets do have some really incredibly turbulent areas. So for Venus to be considered the least hospitable is pretty intense. And part of that is because it has incredibly high pressure. So something up to 90 atmospheres or so, which is about the same that you would experience at a depth of 1 kilometer under our oceans. The planets also, the atmosphere is also composed mostly of carbon dioxide, which of course on our planet we know to be rather toxic to a lot of organisms. Also, it has several kilometers of thick clouds that are composed of sulfuric acid, which is a very unpleasant thing. And this causes a very intense greenhouse effect that causes the surface of the planet to be about 400 Kelvin hotter than it would normally be given its distance from the Sun. So its current temperature is 740 Kelvin, which is so hot that it could actually melt lead. And the surface, just to kind of emphasize this even more, the surface of Venus is hotter than the surface of Mercury, even though Venus is twice as far from the Sun. So like I said, it's a pretty intense place. It also has very strong winds at the tops of the clouds, and actually the winds are so strong that they are almost as intense as those that we find out in the further planets where we have those bands of winds that you can see, like in Jupiter, for example. So some of the winds here can max out at about 350 kilometers per hour. Now, although Venus once had water, it's now incredibly dry. And the surface is made up mostly of rolling plains with a few broad depressions and a couple of highland areas. So it's actually kind of a gentle surface, which maybe goes well with the fact that it's a really extreme atmosphere. You have to have some part of it that's not totally awful to be in. It also has a high plateau that's surrounded by a mountain range, so it also has some interesting topography. And the general lack of small craters on the planet suggests that when there are meteoroids, they burn up in the atmosphere. And where there are craters, this suggests that there were, at some point, a few large meteoroids that broke up in the atmosphere and became really tiny little bits that hit right at the very last minute after they had already broken up into smaller pieces. And so that's why you have these little clusters of craters rather than a few big craters around, which is what we tend to find on our planet. A large portion of Venus's surface is covered by lava flows, and in fact the planet is still volcanically active, but most of the activity is concentrated in just a few spots. And this causes some kind of interesting features. So things like pancake volcanoes, which are eruptions of really thick lava, coronae, which are collapsed domes, or they're thought to be collapsed domes over very large chambers of magma. And some of this stuff isn't really well understood. So I said that the coronae are thought to be those collapsed domes, and that's because we only have a certain number and type of observation, and so this needs to be studied more in detail in the future in order to confirm these kind of theories. Amazingly, despite all this activity, there are still bits of Venus that are incredibly old and untouched, and some of those approach 800 million years old, which is pretty incredible, considering how old our own planet is and how much of the planet gets turned over with tectonic activity and volcanic activity. Now, as you might expect, given that Venus has been known since prehistoric times, it is frequently visible to the naked eye. And in fact, last year we had a rare transit of Venus, which is what happens when you've got the planet directly passing between the Earth and the Sun. And hopefully you got to see that, because the next one is not going to happen until 2117. So maybe some really young babies, if they live quite a long time, will get the chance to see that. Who knows? But Venus is very easy to see, especially if you have binoculars and if you have a nice telescope. And that was Imogen Heap singing Earth. And Earth, the third planet from the Sun, the fifth largest in our solar system, and probably everyone's favorite planetary body, is the next up on our list. And Earth is the only planet whose name does not derive from the Greek and Roman mythology that I've been talking about for the last couple of planets. It actually derives from the Old English word referring to ground or soil. Now, the planet was thought to be an unusual thing in the solar system until about the 16th century, and then people realized that actually it was only one of several planets in our solar system. And although it is, of course, very special to us, it's not special in an astronomical sense, in that there are lots of other planets all doing kind of similar things around the Sun. Now, the Earth is divided into 7 different layers with different and distinct chemical and seismic properties. The bulk of the mass of the Earth is in its mantle and then the core. And the core is predominantly composed, as I kind of mentioned earlier, of iron or of nickel and iron. And maybe there are some lighter elements mixed in as well. And the Earth is thought to potentially be the only planet that has distinct inner and outer cores. However, a lot of our information about these things is only theoretical, and that, of course, is because of the fact that it's really hard to get in there and measure these things, because it's not like we can just sink a thermometer in or sink in a core sample and pull something out. It is very high pressure, it's very hot, it's very difficult to reach, and so we have to do a lot of modeling in order to figure these things out. Now, the temperatures in our core may go up as high as 7,500 Kelvin, which is hotter than the surface of the Sun, so that's pretty impressive. The chemical composition of the entire planet, not just the core and the mantle that I already mentioned, is predominantly iron, again, but then also oxygen, silicon, magnesium, nickel, sulfur, and also titanium. And it is, in fact, the densest major body in the solar system, probably thanks in good part to all of the iron in metals in general that we have everywhere. Now, unlike the other terrestrial planets, we have plates that float separately from the hot mantle underneath them. In other words, we have plate tectonics. And currently we have 8 major plates and about 20 smaller plates. And of course, at the edges of these, that's where you tend to have a lot of volcanic and earthquake types of activities. And because we have all of this activity, we tend to have a very young surface of our planet. And that's why I was saying it was so impressive that the oldest bits of Venus are about 800 million years old, because we find that in lots of our places, the surface properties only last for about 500 million years or so. And that's because the plates are always rubbing up against each other, they're subducting, so one is going over the other, they're getting melted down, they're getting broken up into bits by various processes in the environment. And in the end, we only end up having rocks, really old rocks, that are maybe 4 billion years old in some places. And these are really, really rare. And the age of the Earth is about 4.5 to 4.6 billion years old. And so, to have these rocks that go back almost to that era is really incredible. But most of the time we find that things are only about 500 billion years or so at the max. And one of the most unique properties of Earth is that it's the only planet on which water exists in liquid form. And that, of course, is why it's the only planet on which we know of life. Now, water makes up 71% of the Earth's surface, and one of the things that's interesting to note about that is that it doesn't make up 71% of the Earth, because you do have to think about the fact that you've got really deep valleys in the ocean, and you've got really high mountains on the land, and so you have to take into consideration the area over which these things expand, so how much volume there is and how much weight is associated with those. So sometimes you'll hear people say that water is 71% of the Earth total, but actually it's only 71% of the surface if you're looking down and you would then see 71% waves, and the other 29% being the land masses. And all of this water is important for generating and maintaining life, and also for keeping the temperatures nice and stable, because the water does absorb heat from the sun and also dissipates heat again, but because of the way that it does this, it ends up keeping the temperatures at kind of a nice neutral instead of bouncing around really wildly like we see on some of the other planets. Water is also really active in erosion and weathering, and these are unique processes that we see throughout the solar system, at least in the modern era of our solar system, because we're the only planet that has water available to engage in these activities and shape the landscape in the way that it does. Now, as you have probably already heard at some point or another, our atmosphere is predominantly nitrogen, but then also some oxygen and traces of other things like argon and carbon dioxide, of course, and also water. Carbon dioxide is quite important because it is what keeps our surface temperature comfortable. And of course, this is through the greenhouse effect. And without carbon dioxide, it would be about 35 degrees cooler at any given time. So we'd have an average of about negative 21 degrees Celsius instead of the current global average that we have of 14 degrees Celsius. And at negative 21, we actually would see the oceans freezing. So a little bit of carbon dioxide in the atmosphere is really nice. Too much carbon dioxide in the atmosphere, of course, you have the greenhouse effect, and we would turn into Venus potentially. So we don't want to go to that extreme, but we do want to appreciate the carbon dioxide that we do have, since it does keep us comfortable. And the presence of oxygen in the atmosphere is also quite an interesting and kind of remarkable thing, because oxygen does tend to be a really reactive chemical. Only in the presence of life can we have oxygen the way that we do, because we're constantly generating oxygen, using oxygen and generating carbon dioxide from it. And so we have this big turnover of oxygen. And it probably didn't emerge to the extent that it's now found in our atmosphere until until we emerged, but of course our ancestors would have emerged and learned to do something with the carbon dioxide and extract oxygen in some way, and then change the properties of the atmosphere until it was what we found today. of course, you already know the Earth has a satellite. In fact, it has lots of satellites, but only one of these is natural, and that, of course, is the Moon. But we have put up hundreds of other satellites as well, and you actually can see them in the night sky sometimes. And I didn't know this for a really long time, and then I took an astronomy course when I was in high school. And it was really incredible to go out, and you'd be looking at the stars, you'd be looking at the planets, and all of a sudden you'd see something that was moving quite rapidly. It wasn't blinking, it wasn't a plane, it was very high up and quite small and kind of silvery. And this is a satellite, and you actually can find them pretty easy now that there are so many of them. That was back, 10, 15 years ago, when satellites weren't nearly as numerous as they are now, and you could find them really easily. So I'm sure if you went out tonight and looked for long enough, assuming of course there weren't any clouds, you would be able to find a satellite at some point. The Moon is actually very well studied. It's the second brightest object in the sky, and it's so large that it's sometimes also been argued that it should be classified as a planet, and that the Earth and the Moon should be considered a dual planetary system. It was first visited in 1959 by the Soviet spacecraft Luna 2, and it is in fact the only extraterrestrial body that has been visited by humans. And all of the visitations occurred between July 1969 and December 1972. And during that time, a dozen different people got to walk on the Moon's surface, which must have been incredible. And all of those, sadly, well, not sadly to them, but all of those were men, so hopefully we'll have a day when there will also be a woman that gets to be out there walking on the surface of the Moon. I would love to volunteer myself, but I'm not sure I could really manage the ride. I do tend to get a little motion sick. But the Moon is also quite interesting because it's the only extraterrestrial body from which we've been able to collect samples and return them to the Earth. Now, of course, we do have the rover on Mars right now that's collecting samples, but so far only the Moon has been brought back to us so that we can actually study it here on Earth. And because the Earth is orbiting the Sun at the same time that the Moon is orbiting the Earth, that means that there's actually a slight discrepancy between orbital period and successive new moons. And this was something I didn't know about at all until I was studying, reading up on this to talk about it here on the radio. So an orbit, of course, takes about a month, but a new moon occurs every 29 and a half days. And of course that is quite close to a month, so you probably wouldn't notice this unless you were really taking notes and really paying attention. But all the same, you do have this discrepancy between when the orbit is starting and when we actually see a new moon. Or I should say, a new moon. The gravitational pull of the Moon on the Earth is significant. This is something I mentioned a little bit before when I was talking about the tides and the seasons. So of course this gravitational pull does result in the tides, and it also causes the Earth to bulge a little bit. And the bulge happens where you've got one direction, one in the direction of the Moon, and then you've got another bulge directly opposite. And I think, though I'm not 100% sure, maybe someone out there will know this a bit better, that basically what you've got is kind of a flattening at the poles a little bit because the Moon is pulling the Earth towards us. And so you end up getting this kind of egg shape of the Earth. Well, not egg, I guess, because it's different on one end than the other, but you know what I mean. So you've got a bit of a pull towards the Moon, it's flattening it out and kind of elongating it, kind of a rugby ball or football, American football shape. And you also find that the Earth is rotating faster than the Moon is moving in its orbit, and that means that you've got bulges moving around the Earth once a day. And this is what causes the two high tides. And this is something that we explain to our students every year when we take them on a field course to the Isles of Scilly. And I never quite capture the meaning of all that and how it all worked until I finally read about it preparing for this. And so I'm really glad that I finally have wrapped my mind around this so I can explain it and not feel like a charlatan. Now, the force between the Earth and the Moon is not exactly along the line between their two centers. And that means that you've got torque that's produced on the Earth and also acceleration on the Moon. And to be honest, the physics of this is kind of beyond me. But you just take my word for it that the net result of this interaction is that you've got a transfer of rotational energy from the Earth to the Moon. And this gradually slows down the Earth's rotation. So by about, so every century you have about 1.5 milliseconds variation, and the Earth slows down just a little bit. And of course this is not something that you would ever notice in practicality, but it's kind of interesting to do the number crunching and look at what change has happened over time. So 900 million years ago, we didn't have 365 days a year, or 365.25 to be accurate. There were in fact 481 days, and the days weren't 24 hours long, they were 18 hours long. And so we had a very different schedule here on the Earth. And also, this whole thing doesn't just change the Earth, it also changes the Moon, and it raises the Moon into a higher orbit by about 3.8 centimeters per year, which is actually a bit more noticeable, well, quite a bit more noticeable than the changes on the Earth's rotation. And what's kind of cool about this is that actually, in the past, the Earth had the same impact on the Moon because the positions were reversed, not physically speaking, metaphorically speaking. So the Earth caused the Moon's rotation rate to slow down until it matched its orbital period. And as I mentioned earlier, there is a synchronous rotation, so the same side of the Moon is always facing the Earth. So there isn't actually a dark side of the Moon, it's just that there's a side of the Moon that we never get to see. And this has also happened, all of this has happened elsewhere in the solar system. We're not the only instance in which this kind of partnership occurs. And based on what we know about those other bodies elsewhere, we can calculate that the Earth will, in fact, eventually continue to slow until it matches the Moon's period, and the two of us are in sync. The Moon, of course, has no atmosphere, but it does have, or it may have ice and deep craters near its poles. So even though there's no atmosphere and it is going to be exposed to space, it is still able to retain some water, probably in ice form. It also has an inactive interior, and the center of its mass is offset from its geometric center by about 2 kilometers, and that's in the direction of Earth. It also has a thinner crust in that direction, and no one really understands why this is, but they think it potentially may have something to do with the pull of the Earth on the Moon, either now or in the past, when maybe conditions were a bit different. The lunar terrain has it can be categorized in 2 different ways. So there are highlands, which have lots of craters, and then there are the maria, which are relatively smooth. And the maria are actually impact craters that were then flooded with molten lava back when the Moon was more active. And these are all concentrated on the near side of the Moon, so the side that we see, and they make up about 16% of its surface. And even, of course, you have noticed this probably, without binoculars or telescope, you can in fact see these things with your bare eyes. And the surface of the Moon is predominantly covered with something called regolith, and this is a mixture of dust and debris that's caused by meteor strikes. And this is what was collected when we sent up spacecraft to bring these things back. And in fact, about 400 kilograms of rock samples were returned to the Earth for more detailed study, and the rocks that were dated were found to be somewhere in the realm of 4.6 to 3 billion years old, which is amazing because that's about exactly where our samples peak. As I said, the oldest things for us are about 4 billion years old or so. And so looking at these samples from the Moon means that we're able to get some information about a period of the solar system that can't really be studied here in detail on Earth itself. Now, the origin of the Moon has been debated for a while, but people now think that the most likely explanation is something called the impact theory. And this states that the Earth collided with a really large object, so something the size of Mars or even bigger, and there was material that was ejected from that collision and kind of scattered throughout the solar system, and one big hunk of that material formed the Moon, or maybe lots of hunks that were then kind of compacted together to form the Moon. Now, the Moon doesn't currently have a magnetic field, but some of its surface rocks do show signs of magnetism, and this suggests that there was a field present potentially early on in the Moon's history. And because it doesn't have any of these nice protecting, atmospheres or magnetic fields, it does have a surface that's very much exposed to the solar wind and all the stuff that the wind brings with it. And ions from this have become embedded in the regolith, and that means that when we have all these nice samples, we're able to then study. And if you remember when I talked last week about the sun, the solar winds and the solar flares and all these kind of weird and unusual things that the sun does, these are really of interest to us because we don't know much about them. So being able to study them from the Moon and the samples we brought back from the Moon is a pretty handy thing. That was Enya singing Shepherd Moons. That's a song from my childhood. I have to admit, I know that's kind of jarring considering what I usually play, but I just couldn't resist. Now the last planet on our list today, the last of the inner planets before we move out to the gas giants, is Mars. And Mars is the fourth planet from the Sun and also the seventh largest. It is named after the Greek god of war, or, if you prefer, the Roman god of agriculture. I prefer the first because this is my zodiac sign, and so I like to think of myself as being a bit warlike at some times. Mars is also known as the Red Planet, and it is responsible for the name March, which makes a lot of sense because actually the zodiac sign Aries for Mars is found in kind of the March-April range. I'm an April birthday myself, and of course that makes sense for Mars to also name a month during that time of the year. Now, even though Mars is relatively close to us, it is so hard, it's so small that it's hard to see it in much detail, even with large telescopes. And it's also accompanied by two very small moons that are equally, or perhaps even more difficult to see, and they are named Phobos and Deimos. Now, Mars has a really widely varying climate because it does have quite an elliptical orbit, which means that, like some of the inner planets, it's not nice and circular, but in fact it goes quite far away and then comes back and can be very close again to the Earth. And between the aphelion and the perihelion, so the farthest away and the closest, it can fluctuate 30 degrees Celsius, which is pretty impressive. Mars is much smaller than Earth, but it does have about the same amount of surface area, and that's because, surface area I should say, devoted to land. So we have a whole bunch of water that of course Mars doesn't have, and if you took away all of our water and just counted the bits of land that you can currently see floating above that, that would approximately equal what Mars has. Now it has some really amazingly variable terrain, perhaps some of the most variable terrain in the solar system, and also some really impressive features. One of these is the Olympus Mons, and this is the largest mountain in our entire solar system, and it is a whopping 24 kilometers high, with a base that's 500 kilometers in diameter. Also there is the Valles Marineris, and I'm probably butchering these words horribly. I'm very sorry if there's anyone out there who actually knows how these are pronounced. And this is a system of canyons that's about 4,000 kilometers long and 2 to 7 kilometers deep. Another really interesting feature is the Hellas Planitia, which is an impact crater, from something that came from outer space and landed on Mars. And it is it's at least 6 kilometers deep and 2,000 kilometers in diameter. So it's had a lot of stuff going on its surface and has some very interesting features for anyone who wants to whip out a telescope and try to get a better view. And much of the surface is very cold, I can't talk tonight. It's very old and cratered, but there are also some younger areas as well. Now, very little is actually known about the Martian interior except by inference, and this is because it is quite difficult to see. So we've gotten some data from spacecraft that have flown past, and of course now we're getting a lot of data from the rover, and so maybe our knowledge of this will improve quite a bit. So it appears for now that it has a fairly low density core that probably contains quite a lot of sulfur and also some iron, like our own core. And it does not seem to have any active plate tectonics, although potentially maybe it does, and we just haven't seen them. But what we do know is that there are these really hot spots that are concentrated under the crust, because without the tectonics to kind of allow that energy to dissipate, you have all this concentration in a few spots. And these might be responsible for something known as the tharsis, which is a huge bulge that's seen on the Martian surface, and it's about 4,000 kilometers across and about 10 kilometers high. And no one really knows exactly what this is, except that it does maybe represent a spot where all this energy is trying to come free, but it can't, and so it's pushing out the surface of the planet. Now, overall, this lack of plate tectonics is also quite important for the atmosphere of Mars, which sounds, I know, kind of weird, but when you have plate tectonics, it allows you to recycle the carbon dioxide from the rocks back into the atmosphere. So carbonate rocks are rocks that contain a lot of carbon, and when they're ground up, then all those molecules can be released again and eventually go back up into the atmosphere to be incorporated elsewhere. And of course, you know all of this like the back of your hand, because I talked about some of this cycling a few weeks ago before we broke for Christmas. So because of all this, the upshot is that there isn't this carbon and carbon dioxide up in the atmosphere, and that means there's not a greenhouse effect. And so that means that they have a much colder temperature than, for instance, the Earth would have at that same distance because we have this nice atmosphere that we do have. Now, the signs of erosion on Mars's surface make it clear that it did once have rivers, and it probably even experienced floods, although the liquid that did all this may not have actually been water. It might have been some other type of element. Mars does also currently have ice caps at both of its poles, which is quite an interesting thing for people who are interested in settling there and potentially pursuing terraforming and human colonies. Overall, the atmosphere of Mars is quite thin and the pressure is quite low. And in fact, despite this thinness, it is thick enough to allow very strong winds and giant, quite long and intense dust storms, which maybe could suggest that some of those terraformers may not find it quite as nice as they would like, despite the presence of water. The planet does also have very large but weak magnetic fields in some areas, and these are probably remnants of an earlier global field that encompassed the entire planet. And this is interesting because it may have impacted the atmosphere of the planet and maybe potentially made it more suitable for life back in the day whenever there was a magnetosphere around the entire planet of Mars. And there aren't any signs of organisms yet, although there have been some reports that some of the meteorites that were thought to originate on Mars also did contain microbes, but this has been hotly contested, and a lot of people have said that actually that's just contamination. And this is one of the many things that the Curiosity rover is going to be investigating as it churns its way across Mars and picks up rocks and bites through them and kind of takes them apart and does all these chemical analyses. And actually, if you are not already, I really suggest that you follow the rover on Twitter and check out the webpage, because it does periodically send out updates to kind of talk a little bit about what it has found. And I'm talking about it like it's a real thing, but of course it's the people who are analyzing the data. But it is quite an exciting thing to get these little updates and read about them as they are coming in, and we are finding more about the red planets. And that concludes today's program, thus the last of the inner planets. And I will end up here with the Weepies singing Orbiting, and next week I will move on to the outer planets. So I will talk to you then.